All right, let's talk about a piece of tech that is so fundamental to our lives, you probably don't even think about it. It's pretty much everywhere, but it's almost totally invisible. We're pulling back the curtain on the unsung hero of the modern world, optoelectronics. So, to get us started, let me ask you something. Think about your TV remote for a sec, or a Blu ray player if you still have one. How about the fiber internet that's likely streaming this to you right now? What is the one thing that connects all of them? You guessed it, the answer is optoelectronics. And what is that? Well, just think of it like this. It's the technology that builds a bridge between electricity and light. It lets them talk to each other, to literally turn one into the other. And in doing that, it basically powers our entire digital world. Okay, so how does this bridge actually work? It's not a one-way street, that's for sure. Optoelectronic devices are really built to do one of two things. They either take electricity and create light out of it, or they see light and turn it right back into electricity. So we can kind of split them into a few groups. First, you got your emitters. These are things like LEDs and lasers, and they do exactly what it sounds like. They emit light from electricity. Then you've got detectors, like photodiodes, which do the complete opposite. They detect light and create an electrical signal from it. And there's also a third category, transducers, think solar cells, which convert light into other kinds of energy. For right now, though, we're going to focus on those first two, the emitters and the detectors. But look, before we get into the cool gadgets, we have to understand the basic rules of the game. And that means we need to take a quick peek at the physics of how light, which is just a stream of tiny particles called photons, actually talks to matter on an atomic level. It really boils down to three key interactions. First, there's absorption. A photon comes in, zaps an atom, and an electron inside that atom gets all hyped up and jumps to a higher energy level. Easy enough. Second, we have spontaneous emission. That excited electron can't stay hyped forever, so it eventually calms down, falls back to its original spot, and spits out a new photon in some totally random direction. This is the key to how LEDs work. And then number three, this is the really cool one, stimulated emission. This is where a photon comes along and kind of nudges an electron that's already excited. That nudge makes it fall and release a second photon that is a perfect, identical clone of the first one. And that is the secret sauce behind the laser. And that difference right there is everything. Spontaneous emission is completely random and chaotic. Think of a big crowd where everyone is just clapping whenever they feel like it, but stimulated emission, that's ordered, it's synchronized. It's that same crowd clapping in perfect thundering unison. One gives you a tiny indicator light, the other gives you a beam that can cut through steel. It's a huge difference. So let's see how we actually use this stuff to make our light emitters. We're going to see how we take these two very different types of emission and create two very different but equally important light sources, the LED and the laser. So first up is the humble LED, the light-emitting diode. It's a really clever little semiconductor that you feed some electricity to. And through that process of spontaneous emission we just talked about, it turns that energy directly into light. It's super efficient, it's cheap to make, and because the emission is random, the light just kind of spreads out everywhere. The laser, though, that's a completely different animal. It's capable of so much more. But why? Well, the secret to its incredible power is actually hidden right there in its name. See, laser isn't just a word, it's an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. And the most important part is right there in the middle, stimulated emission. A laser is a machine built for one purpose, to create a massive runaway chain reaction of this process, which amplifies light into something incredibly powerful and precise. And the light that comes out is just different, totally transformed. Ordinary light, like from an LED, has a bunch of different colors mixed together. The light waves are a total mess, and it spreads out fast. Laser light is the exact opposite. It's monochromatic, it's one pure color. It's coherent, all the waves are perfectly in sync, marching together like a tiny army. It's directional, it's a super tight beam that goes exactly where you point it. And because of all that, it is intensely powerful. So how do you actually build one of these things? Well, you need a three-part recipe. First, you need an active medium. That's the stuff whose atoms you're going to get all excited. Second, a pumping scheme. That's just the energy source you use to get them excited. And third, the secret ingredient, an optical resonator. This is basically just two mirrors that trap the first photons, bouncing them back and forth through the medium over and over again, creating more and more clones until the beam is strong enough to burst out. Okay, so we've got creating light down. Now let's flip the coin over. How do we see that light? How do we catch it and turn it back into a useful electrical signal? Well, welcome to the world of detectors. And the hero on this side of the story is the photodiode. You can really just think of it as a tiny electronic eye. It's a special semiconductor that when light hits it, it instantly creates an electrical current. The brighter the light, the stronger the current. But of course, not all electronic eyes are created equal. The tech has gotten a lot better over time. You had the original, the PN photodiode. It works fine for simple stuff, but it's a little slow and not great at seeing dim light. So engineers came up with an upgrade, the PN photodiode. They stuck a special intrinsic layer in the middle, that's the eye in PN, and it acts like a much bigger net for catching photons. That makes it way faster and more sensitive. But for the really, really tough jobs, like picking up a weak signal at the end of a long fiber optic cable, you need to call in the specialist, the Avalanche Photodiode, or APD. It actually has a built-in amplifier, so it can detect even the faintest whisper of light. So here's the big takeaway. We now have a way to make light, and we have a way to see light. And when you put those two pieces of the puzzle together, well, that's when you unlock basically all the technology that defines our modern world. The equation is just beautifully simple. You take an emitter, like a laser, and you pair it with a detector, like a super fast photodiode. And what does that give you? The foundation of all modern communication. The laser flashes on and off billions of times a second, creating a code of ones and zeros. And the photodiode at the other end reads it perfectly. And once you know what you're looking for, you realize this principle is absolutely everywhere. It's the fiber optic cables that are the backbone of the internet. It's in your Blu-ray player, your TV remote, barcode scanners. It's all over the medical field, from laser surgery to the little clip they put on your finger to measure your pulse. It's in factories, in your smoke detectors. It's just everywhere. I mean, when you really stop and think about it, it's pretty mind-blowing. This entire global technological ecosystem is built on our ability to control the behavior of a single photon. Optoelectronics is like the universal translator that turns the pure physical language of light into the practical digital language of data. And that brings us right to the future. Our world's appetite for faster data and smarter sensors is never-ending. And the foundation for all of that future innovation is going to be built on this bridge between electricity and light. So the real question isn't if this technology will be important, but rather, what are we going to ask light to do for us next?